All right, lesson 7.3 is solving linear systems by adding or subtracting. Before we solve linear systems by graphing, and then our second method was substitution, now we have a third method called using elimination. In my opinion, this method is the quickest method, and I think most of you are going to choose this method if you are given a choice. When solving a linear system, you can sometimes add or subtract the equations to get a new equation that has just one variable in it. This method is called elimination. You should write down these 3 steps. The first step is to add or subtract the equations to eliminate one of the variables. Once you have the new equation, you can solve that new equation for the other variable, the one that you didn't eliminate. And lastly, once you have that variable solved for, you can put it back into either of the original equations to get your eliminated variable. So here we go. We have the equation 2x plus 3y equals 11 and negative 2x plus 5y equals 13. I look to see, do I have either the exact same or the exact opposite variable terms. In this case, I have the exact opposite x terms, and to eliminate exact opposites, you add. 2x plus negative 2x is gone. 3y plus positive 5y is 8y. And 11 plus 13 is 24. Now I'll divide by the 8, and y equals 3. So that was pretty quick. Now I'm going to take the y equals 3 and put it either into the top or the bottom equation. It doesn't matter which one you choose. I'm going to put it into the top one. So 2x plus 3 times 3 equals 11. So 2x plus 9 equals 11. I'll subtract off the 9 to get 2x equals 2. Divide by 2 and x equals 1. So my ordered pair is 1, 3. And that was pretty quick. Here's another one. 4x plus 3y equals 2. 5x plus 3y equals negative 2. I don't care that I have exact opposite constant terms. I only am interested in the variable terms. So here my y terms are exactly the same. Well, if they're exactly the same, to eliminate them, I'm going to subtract. But when you subtract, you're really adding the opposite of everything. I prefer to change everything to addition. So I'm going to say, add the opposite, opposite, opposite. We only change the equation that we're technically subtracting. I don't do anything to this top equation. So 4x plus negative 5x is negative 1x. 3y plus negative 3y drops. 2 plus positive 2 is 4. Divide by the negative 1, and I get a negative 4 for x. I've solved that one. Now I want to solve for the eliminated one. I will put this in my top equation just because I'm a creature of habit and that's where I generally put it. Plus 3y equals 2. I'm solving this equation for y. I get negative 16 plus 3y equals 2. Add 16 to both sides, so 3y equals 18. Divide by 3 and y equals 6. So negative 4, 6. Sometimes you have to arrange the like terms. So really we want to put them in standard form. Standard form is ax plus by equals c. So if I look, the top equation's already there, so I'll just rewrite it down here. My bottom equation, I need to move the x term over to the left-hand side with the y. So to move it, I'm going to subtract it. So negative 3x plus 4y equals 14. Now I have exact opposite y terms, so I will add. 8 plus negative 3x is 5x. The y terms eliminate. Negative 4 plus 14 is 10. Divide by 5 and x is 2. will put x is 2 in the top equation again. 8 times 2 minus 4y equals negative 4. 16 minus 4y equals negative 4. I will subtract 16, making sure I bring down the negative with the 4y, so be careful of that. When I subtract 16, I get negative 20, divide by negative 4, and y equals 5. So my ordered pair is 2, 5. Last example I have for you is an application problem dealing with a fishing barge. A fishing barge, a big boat, leaves from a dock and moves upstream against the current. That means it's fighting against the current, so it's going to slow it down a little bit. The boat in the current is moving at a rate of 3.8 miles per hour until it reaches its destination. After all the people on the barge are done fishing, it moves the same distance downstream, but now it's going with the current, so it goes a little bit faster. Now it's at 8 miles per hour until it reaches the dock. The speed of the current remains constant, so the speed of the current didn't change at all. We're going to use these models to write and solve a system of equations to find the average speed of the barge in still water and the speed of the current. So I'm going to call, I've got the upstream and downstream equations. The speed of the barge in still water, I'm just going to call x, minus the speed of the current, I'm going to call y, and the speed of the barge upstream is 3.8 miles per hour. Downstream, my speed of the barge is still x. Now it's going with the current, so I'm going to add the y. And the speed of the barge is faster. It's 8 miles per hour. So I'll put the equations a little bit closer to each other. And I have a choice now. I have exact same x terms, so I could subtract. I have exact opposite y terms, so I can add. I prefer adding because then I don't have to change anything. So I'm going to add x plus x is 2x. The y's drop. 3.8 plus 8 is 11.8. Now you just divide by 2 and you get 5.9 miles per hour. So that's the speed of the barge in still water, 5.9 miles per hour. Now I will put this back into, I could put it in either equation. This time I'm going to actually put it into the bottom equation because I notice there's a positive x here, so I'm not going to have to divide by negative 1 when I'm done. It doesn't matter though, you could still put it in the top equation. I get a 5.9 plus y equals 8. I'm going to subtract 5.9 from both sides, and I end up with y equals 2.1 miles per hour. So the speed of the barge in still water is 5.9 miles per hour, and the speed of the current is 2.1 miles per hour. This concludes your notes on lesson 7.3. Make sure that you come in with the notes having been taken and then ask your questions, and hopefully you'll have a lot of time to work in class.